Hi, welcome again to this course on control theory. So we are now in the second session. We will discuss mathematical modeling of dynamic systems. Okay, in the previous session, we have already discussed the Laplace transform, and also before that, we introduced you the concept of dynamic systems. We are now moving to the next topic on modeling. So this will be the learning objectives of this session. So by the end of this session, you should be able to define different types of model, mathematical model for dynamic systems. You should be able also to translate one model to another type of models. And then you should be able also at the end to derive a transfer function from a block diagram model. So the first question that might appear in all of us heads is, why do we need a mathematical model of a dynamic system? Of course, here we are talking about designing a controller. The ultimate goal of this course, we will learn on how to design a controller for a particular system. But it's like a fashion designer. Let's say if there is a fashion designer, he designed a cloth for you, that he or she, the fashion designer, he needs to have a model of yourself, the length of the sleeve, the any dimension of yourself. So he needs that model, he or she needs that model in order to help him to design the fashion for you, right? So same thing to this, controller is unique to the system. So in order to help us as the controller designer to design a controller, we also need to have the model of the system that we want to control. Okay. So in short, then a controller design specification are quantitatively described, and it requires a mathematical model of the system. We need to study the system. Of course, we need to analyze. At the end, you should be able to control the system for different types of systems. System can be anything, can be mechanical, electrical system, hydraulic system. We discussed this in the previous session, of course. And we need also to understand how different system will respond to any inputs. There are many types of input that you can give to the system, and then you need to understand on how this system will respond to different inputs. And this will help us also to design system parameters based on the system response that you might have. Okay, so talking about system model, there are many numbers of mathematical model of a system, of a dynamic system in particular. But in this session, we particularly will discuss only three different types of modeling. Those are differential equation. We touched this a bit in the previous session. But there are also two different types of modeling, which are transfer function and block diagram. We will discuss all of these three in the next few slides. Okay, we have already discussed about the first type of system, which is the differential equation last week. So let's move to the second type of the model, which is a transfer function. What is transfer function? So the easiest way to describe it by taking an example. Let's consider a thermometer. Okay, let's consider again specifically a body thermometer. So a thermometer that you use to measure your body temperature. If you use this body thermometer, what you will do, you are going to measure the temperature of your body. That means you are giving an input of temperature of your body to that thermometer, right? And then the output will be, let's take a case next for example, mercury type thermometer. The output of this thermometer will be the level of the mercury in your thermometer. So the input is your temperature body, the output is the mercury level on your thermometer. So to model it in differential equation, the one that we have already discussed in the previous session, the model of this thermometer will be shown in this equation. So this is the model of the differential equation model of the thermometer, where Qi is the input entity, which is the body temperature, let's say, and Q naught is the output of the thermometer, which is, in our case again, is the level of the mercury. If you look at this model, this differential equation involves Qi, the input, Q naught, the output, but it also involves the first derivative of Q naught, the output. So if you see here, the first term is the first derivative of the output. Of course, from this equation, because it involves the derivatives of the output, this is a differential equation model. Now we want to transform this model in differential equation form to a transfer function form. How to do that? Step by step wise on how to transform differential equation to transfer function is like follow. First, you Laplace transform the differential equation. So if you look at the right hand side, there is an entity of the input signal Qi. Let's assume that the Laplace of this Qi in time domain is the capital Qi s. So this is the Laplace of Qi in time domain. So in the right side, you will have k, one of the constant in the differential equation, times the Qis. The next term is the output Q naught. So let's assume the Laplace of Q naught is the capital Q naught s. This is the Laplace of lowercase q naught, the Q naught in time domain. And then the most left term is tau Q naught dot. You still remember when we discussed about Laplace transform, how to Laplace the first derivative of a function. So Laplace of Q naught dot will be equal to S times capital Q naught minus the initial value of Q naught, the value of Q naught t when t is equal to 0. And of course, you have to multiply it by the one of the constant there, tau. So this is what you have seen in the last equation here is the Laplace of the differential equation of the model. That is the first step. You have to Laplace the differential equation. And then the next step is you have to assume 0 to all initial condition. What do I mean by initial condition is the value of either Qi or Q naught when time is equal to 0, including their derivatives. So in this equation, in the last equation here, we only have one initial condition, which is Q naught 0. The Q naught when time is equal to 0. You might have other initial condition in this Laplace of the differential equation, but in this particular case, we only have one terms of initial condition. What you have to do now, you have to set the initial condition, all initial condition, if there are more than one, you have to set it to 0. So I will set it to 0, so I can neglect this part. So I remove this part, and then I can do some mathematical manipulation. I will get something like this, right? After I remove Q naught. But please note, in this equation, I just remove the term S between bracket just to simplify my writing. I just remove that. I just omit the S between bracket. So my equation is becoming like this. And then what next? You still remember Qi is the input in Laplace domain. Q naught is the output in Laplace domain. When you want to form the transfer function, what you have to do? You have to take the ratio of the output and input in Laplace domain. The output in Laplace domain is Q naught. The input in Laplace domain is Qi. So I take the ratio between Q naught and Qi, which is becoming k over tau s plus 1. So this is the transfer function form of the model of the thermometer. So this is another representation of the model. Beside the differential equation, you can model it as a transfer function like this. So let's call here this equation Gs, a function of S, is the transfer function of our system, of our thermometer in this case. Okay? Okay, now the question is how a transfer function will help us in understanding the system. We have already discussed in the previous slide that transfer function is the ratio between output and input in Laplace domain by assuming all the initial conditions equal to 0. So, as expressed in this equation, the Laplace transform, let's say the Laplace transform of the ratio between output and input, which is the transfer function, let's call it GS here. So the transfer function is equal to the ratio between output, let's call it CS here, and input R in here. Both of them are in a Laplace domain. So how this will help us in understanding the system? From this relationship, we know that GS is equal to CS over RS. In such, if you know the input that you give to the system and you know the transfer function of the system, you can immediately evaluate the output of the system. From this expression, you know that GS is equal to CS over RS. So the output CS, you can immediately find it by taking CS equal to the transfer function GS times the input RS. The input, of course, here is also in Laplace domain. So from this expression, from the last equation, CS equal to GS times RS, we can find the output of the system. But remember here, the output is still in Laplace domain. If you want to find the real output in time domain, after you obtain this output in Laplace domain, you have to inverse Laplace it back to time domain, and then you will get the response, the output in time domain, CT. In the previous few slides, we have already discussed a second type of the model of a dynamic system, which is transfer function. As I have already discussed in the very first slide, that there are three different approaches of modeling. The last one is block diagram. So what is block diagram? Block diagram is nothing more just a pictorial representation of a transfer function. So as you can see in this first drawing here, there is a system here which is represented by a transfer function. And then as you can see in this drawing, there is one arrow pointing to the system, which is indicated by RS. RS represent the input, and on the other side you have CS. CS represent the output of the system. So if you look at this simple block diagram like this, how to interpret this? To interpret this block diagram, you just simply conclude that you have a system with a transfer function of GS. To the system, an input of R is given to the system, and because of this input, the system will give an output of CS. And then mathematically, how to interpret this drawing? It's just same as the transfer function model. To interpret this kind of block, you can use the equation that is shown in the last part of this slide. So C output is equal to G, the transfer function of the system, times the input R. So this is how to interpret the block diagram in mathematical manner. Okay, now let's talk a bit more detail about model of a dynamic system. In the example of the thermometer that we just discussed before, if you can go back to that slide, you can see that the differential equation that represent the thermometer, it involves the input Qi, the output Q naught, and the first derivative of the output Q naught dot. But that is considered to be a simple model of a dynamic system. In fact, you might have a very complex dynamic system that also involves not only the first derivative of the output, but you might have a second derivative, third derivative, fourth derivative, and any order of derivatives of the output. But at the same time, your differential equation might also involve any derivatives of the input as well. So in this differential equation, the generic form of differential equation that you can see in this slide, you can consider x as an input to the system, y is the output. If you look at this differential equation, the differential equation involves the first derivative of the input, somewhere here second derivative, third derivative, until m minus 1 derivatives of the input, and until the mth derivatives of the input. At the same time, this equation also involves the first derivative of the output, second probably here, third, until nth derivatives of the output in here. So this basically is the generic form of differential equation to represent a dynamic system. Okay. Now, how to transform this differential equation to a transfer function form? We use exactly the same methodology like the one that we discussed before when we transform the differential equation of thermometer to transfer function form. So what we do, we Laplace transform the differential equation. Okay, if you Laplace transform it and you set 0 to all of the initial condition, you will get this expression. Okay, where x, the capital X here, is the Laplace of the input x, and capital Y here is the Laplace of the output y. Okay, and then what next? You still remember when you want to form the transfer function, you have to take the ratio between output y and the input x. So by simple mathematical manipulation here, you only have a algebraic equation here, so you can find the ratio between output y and input x in Laplace domain, which will be equal to this equation. So basically, this is the transfer function form of any generic form of differential equation, and this will become the transfer function of this generic dynamic system. In block diagram, of course, once you have the transfer function of the system in block diagram, you can just simply put the transfer function equation on the block of the system, and then to the system, of course, you might have an input R, and then the system will respond it by giving an output C. So the block diagram representation of that generic system will be as you can see in this slide. Let's take a bit more illustration on an example. So this is a typical problem in mechanical system. If you look at the drawing on the right side of this slide, how do you see this? Basically, you have mass, block of mass. The mass is supported to the ground through a spring with a spring constant of K and a damper of B. Okay, so you can imagine this as a wheel of your motorbike. If you hold the motorbike, the wheel will be hang supported by the shock absorber, and basically shock absorber is the combination of spring and damper. So this looks like a, let's say, front wheel of your motorbike. Now imagine if the mass M there, you excite this mass with a certain dynamic force Ft. Imagine if you have a system like this, what will happen to this mass? This mass will be displaced by x. So x represent the displacement, the motion of the mass, while Ft represent the force that you use to excite the mass. So intuitively, of course, you can see this as a system that consists mass, spring, and damper, and you give an input of Ft. The input to your system is F, and then the system will respond it by giving an output of X by displacing the mass. So X is the output, F is the input to the system. To derive the relationship between output X and input F, the model in differential equation can be represented as in this equation. Okay. We are not going to discuss in here now on how to derive this equation. We will discuss it later on in the next topic. But anyhow, for time being, just accept this is the model that correlate the input f and output x in here. So you have the model in differential equation form. We are going to transform this differential equation form into transfer function form. So how to do that? You take a Laplace transform to this differential equation and you set 0 to all initial condition that might be there. After you do that, you will get this second equation. If you look at this, the capital F represent the Laplace of the input ft. The capital X represent the output x in time domain. Okay, so you have this expression when you want to find the transfer function. Again, transfer function is just the ratio of the output to the input. The output is x in this case, the input is f, so the ratio is for x over f will be equal to 1 over ms square plus bs plus k. Okay, so this is an example of a real application. What does it mean then? Once you have the transfer function of the system, where again, in our case here, transfer function of the system here is the ratio between the output x and the input f, if you know the force that you give to the mice. And then you can transform this force to the Laplace domain to fs. How to transform it? You just refer to your Laplace table. And then you know the fs. Once you know the fs, you can just simply multiply this to the transfer function. So the transfer function times the force f, you will get the x, the response. But again, the response that you get after you multiply the fs to the transfer function is the response x in Laplace domain. Your response is still in Laplace domain. Refer again to your Laplace table. You can inverse Laplace it, and then you will get the response x in time domain. So that's how the transfer function of a system will help us in analyzing a response of the system. Okay, as I just mentioned, the response can be calculated once your response in Laplace domain is obtained.